So now that we've seen how to find partial derivatives, we're going to start taking a look at being able to apply the partial derivative. And remember in Calculus 1 that we talked about the idea of a tangent line. Well, in Calculus 3, what we're going to do is we're going to utilize a tangent plane to be able to approximate the value of a function in more than one variable. And then we're also going to be able to find the rate of change or approximate that using a total differential. So you might remember in calculus the idea that you were able to find the equation of a tangent line at a specific point, and that line could approximate the value of a function. And the reason we like to use a line is because a line is simple to try to compute. Okay, so in Calc 1, maybe we had something pretty basic. So I'll just give you a basic example. So we have a function f, it's continuous, it's differentiable, and let's say that we're looking at a specific point, and we can draw the equation of, we can find the equation of the line that's tangent at that point. And what we can do is we can use that to maybe approximate the value of f, maybe a little bit further out, or maybe over here, or something like that. That's really close to that point, but not necessarily on that point. In 3 dimensions, what we're going to do is we're going to do the exact same thing, except we're going to have a tangent plane. All right, so maybe we have a shape that looks something like this, and we just have a plane. Maybe we have this point somewhere that's on the surface. Right, so I'll exaggerate the point, and we'll draw a plane that's tangent. Now, when we draw the tangent plane, imagine that that plane is kind of sitting on top. So we have this plane that's sitting just on top. Okay, so it's almost like balanced at a fulcrum point to where it's perfectly placed on top of that function. And let's say for some reason we might want to figure out or approximate the value of the function over here, or maybe down here or something like that. All right, approximate the value. We can use our tangent plane to be able to do that. All right, so the question is, how do we utilize a tangent plane? So remember in Calculus 1 we found the derivative, and we were able to use y equals mx plus b. Well, in Calc 3, what we're going to do is we're going to use y equals mx plus b, except that m is going to have 2 slopes, an m in the y direction and an m in the x direction. And the b is going to be the z-intercept. All right, so essentially what we're doing is we're just extending our concept from Calculus 1, and we're just adding in another dimension into this so we can get a 3-dimensional plane. All right, and I essentially have like a basic overview as to where you could rewrite the equation that's going to be in the general form into this form, okay, which is essentially what you would have done at Calc 1, all right, to be able to find the equation of the tangent plane. All right, and essentially the equation of the tangent plane, which looks like this, is going to be the linearization of that function at a specific point. So really it can just be, z is really the same thing as L of xy. All right, so we're going to take a look at a couple examples, and we're going to try to figure out to what degree of accuracy does this linearization really matter. All right, so if it doesn't really work, then why bother doing it? So a few examples, a pretty basic one to start with. For each curve, find the equation of the tangent line, then find L of xy, which are essentially the same thing. Find the value of fxy and lxy, and then we're going to comment on any disparity that may exist. All right, so we're going to find the equation of the tangent plane to this radical function at the point 2, 1. Then we're going to use that to approximate f of 1.95, 1.08. And we're going to find L of 1.95, 1.08 and approximate the difference. All right, so here's how we're going to do that. Really easy. First of all, z naught is going to be equal to f at the given point. Right? So that's the intercept in this case. And z naught is just going to be the square root of 20 minus 2 square minus 7 times 1 square. That should be 20 minus 11, which is the square root of 9, otherwise known as 3. So it's almost like somebody picked a really nice number for this. Now we need to find the derivative with respect to x. What might be helpful is to rewrite the function as a square root. All right, so let's rewrite this as 20 minus x squared minus 7y squared to the 1/2. And now we can find the derivative. We're going to need a chain rule. So fx is going to be 1/2 of 20 minus x squared minus 7y squared to the minus 1/2. And then we're going to multiply that by our interior derivative of x, negative 2x. Right? Or another nice way to write that, we can cancel those out. We can just move that square root to the bottom, and we can get the opposite of x over the square root of 20 minus x squared minus 7y squared. And what we're going to do is we're going to evaluate this at the given point, 2, 1, to be able to find the slope. Okay, so we're just going to find that at 2, 1 for xy. Remember, we already plugged in 2, 1 into this radical expression. In fact, we just did that up here, and that just gave us 3 as the denominator. All right, so what's really nice is we already know that the denominator is going to be 3 by substituting 2, 1 back in. We have a negative out here, and we know that 2 is the numerator. All right, so this is our fx at 2, 1. Okay, so that basically means the slope in the x direction. Now we need the slope in the y direction. And the derivative is going to be the exact same derivative to start. So it's going to be 1/2 20 minus x squared minus 7y squared to the minus 1/2. But this time we're going to multiply that by the derivative with respect to y of the interior, which is going to be negative 14y. We could simplify that. The 1/2 and the 14 simplify to 7. So we end up with negative 7 over the square root of 20 minus x squared minus 7y squared. And that's going to end up giving us, if we substitute 2 comma, and there should be a y up here, excuse me, so that should be 7y. If we substitute 2, 1 in there, all right, we already know the bottom is going to be 3, and then the numerator is just going to be 7 times 1, which is going to give us negative 7/3. And again, that's going to be our slope in the y direction. So this is fy at 2, 1. And we have all the components that we need. All right, so we have the slope in the y direction, we have the slope in the x direction, and then we also have the y-intercept, or the value that we need, this z0, which is 3. We're going to substitute back into our equation, and remember our equation is going to be all the way up here. And so it's essentially going to be equal to z0 plus the derivative, x minus x0, fy, the derivative y minus y0. Okay, so let's just set this up. Okay, so z is going to be equal to, remember we got 3, which is our f at x0, y0, in other words, z's naught, plus, remember we got negative 2/3, and remember the original point was 2, 1, so it's going to be x minus 2, plus negative 7/3 x minus, or y minus 1, excuse me, not x. So that's going to be a y minus 1. Right. And then finally we can go ahead and distribute and collect a whole bunch of terms. So z is going to be equal to, now if we distribute that 2/3 times 2, and we're going to add to that 7/3, and we're going to add to that 3, we end up with 20/3. So this is the equation I get just by simplifying the above. So it's negative 2/3 x minus 7/3 y plus 20/3. All right, so I just distributed, blah, blah, blah. All right, remember this is our fx, this is our fy. Right, so we just used our formula from before. And by the way, this is exactly what L of y is equal to. All right, so L of xy, which is the local linearization for this, is negative 2/3 x minus 7/3 y plus 20 over 3. All right, so this is our response to part A. So now the next part of the problem, part B, asks us to approximate f at, I think it was 1.95 and 1.08. Let me just verify that. So 1.95, 1.08. So, and to try to find a difference between those. So f at 1.95 and 1.08. Remember, the original function was the square root of 20 minus x squared, which is going to be 1.95 squared, minus 7y squared. And what I'm going to do is I'm going to approximate this to maybe 6 decimal places just to see how far it goes out. So just bear with me while I substitute this in my calculator. And I got 2.83, if I typed everything in correctly, so 2.8342. 420. Right. Now we need to find what L at 1.95, 1.08 is. And this is much easier to find. In fact, if we really wanted to, we could probably do this by hand. Although we're not going to because we got better things to do. Plus 20 thirds. And I'm going to type this in the calculator and see what we get. So negative 2/3, 1.95. Excuse me, it's going to be, yeah, that's good. Alright, and after just a little bit of computation, 2.84667. Alright, so what do we notice? Well, it's not terribly accurate, but at the same time, it's not terribly inaccurate. It looks like it's accurate to at least the tenths place in this example. All right. Now notice that we're 0.05 and 0.08 away from the original point, so there's going to be a little bit of disparity in there. All right. So if we were to make a comment on this, then the comment we would say is that we are accurate or I guess we should be specific about this. So let's say what is accurate. So we can say L 1.95, 1.08 is accurate to the tenths place. All right. And so hopefully you can see the whole genesis as to why we use a linear approximation is because there's sometimes that there's things that are much more difficult to compute. They're transcendental, radical functions, rational functions, right? When a simple linear function can be processed very easily. A lot of times in computer science, we like to run things linearly to try to model these more difficult sort of functions. And so it just cuts down on the runtime, making things much more efficient. Even if it's not necessarily as precise, as long as we're in the ballpark, it's good enough. So we're going to do another one, and then we're going to take a look at the total differential in the next video.